Hi, in this screencast, I'm going to walk you through Project 1, which is about a very interesting problem called percolation. And I'm going to give you some hints along the way on how you may want to approach the project. Okay, so here's the PDF for the project. You can find a link to the PDF on the assignments page of the course website. And on that page, you will also see a link to the zip file for the project, and when you download and extract that zip file in your computer, you're going to see a folder such as this containing these files in it. Okay, so some of the files in there are starter files for the problems in the project, and then you have a file called report.txt that you may want to use as a template when you write your report for the project. And then you have this file called runtest.py that you should use to test your solutions and to make sure that they conform to the input and output specifications. Right? And then there is this folder called data with some sample input files and some reference solutions. Okay, so now let me walk you through the write-up for the project. Okay, so what is this problem of percolation? Well, let's say you have a composite system of some sort with randomly distributed insulating and metallic materials. So a question of interest might be what fraction of the system needs to be metallic so that the composite system is an electrical conductor. Okay, let's take another example of a porous material with some water on the surface. Okay, now here a question of interest might be what are the conditions under which the water will seep through the material and get to the bottom. Okay, now to model such situations, scientists use an abstract process that's called percolation, and it's that process of percolation that we're going to study in this project. Okay, now how do we model a percolation system? Well, we're going to model it as an n by n grid of sites. Okay, so here are two examples of such grids. Now, in such a grid, you're going to have sites that are either open or blocked. Okay, so here, for example, the black cells denote blocked sites and the white cells denote open sites. Okay, now a full site is an open site that is connected to an open site in the top row via a chain of neighboring open sites. All right, and by neighboring we mean cells to the left, right, up, and down. All right. Um, so for example, here is a full site since it is connected to an open site in the top row via a chain of neighboring open sites. Okay, now we say that a system percolates if there is a full site in the bottom row, meaning if we pour something here at the top, then it will reach some of the open sites in the bottom row. Okay, so here is a system that percolates. All right, now this system here does not percolate because if I pour something here at the top, there is no way it's going to reach to any of the open sites in the bottom. Okay, now given an n by n system, um, uh, 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 this is the problem that we want to try and solve. Okay, if the sites are independently set to be open with probability p, or in other words independently set to be blocked with probability 1 minus p, then the question is what is the probability that the system will percolate. All right, now when p is 0, it's obvious that the system will not percolate because in that case all the sites are blocked sites. Whereas if p is 1, then the system percolates because in that case all the sites are open sites. Okay, now this value p is what we call the site vacancy probability. Um, in the plots here, what you see is the site vacancy probability p plotted against the percolation probability of the system. Okay, and as you see, as the site vacancy probability increases, the system switches from not percolating to percolating. Okay, and this transition is sharp for a system that is large. So here you have a 100 by 100 system, which is much larger than 20 by 20 system, which is what you have here. And as you can see, the transition is much sharper here than it is here. Okay, so when n is sufficiently large, there is a threshold value p star. Okay, so a sharp crossover such that when p is less than p star, then the system almost never percolates, but when p is greater than p star, then the system almost always percolates. All right, so it is this threshold value p star that we are after. So it turns out that there is no mathematical solution that is yet known for determining the percolation threshold p star of a system. Okay, so we have to resort to computational means to get an estimate for this value, and that is exactly what we are going to be doing in this project. Okay, now before I proceed, I should say one thing, that if I give you an n by n system such as this, which with a certain value for the site vacancy probability, then you can easily and if I ask you to check whether or not the system percolates, you can easily come up with a solution that uses a set of loops and implements this idea of pouring something here at the top and figuring out whether or not that substance reaches an open site at the bottom. And if it does, then you say that the system percolates, and if it doesn't, you say the system does not percolate. And you can repeat this process for different values of p, and you can get a sense for the percolation threshold p star. Okay, so that's one way to solve this problem, but it turns out that that technique is not approach is not efficient at all, especially it's no good for large systems. Okay, so that's not the approach that we are going to follow. Instead, we will use a very interesting and a sophisticated data structure called the UnionFind data structure to implement our solution. Okay, so with that kind of background, let's now talk about the first problem, which is about modeling a percolation system. Okay, so to model a percolation system, what we need to do is create a data type called percolation in the file that's called percolation.java. Okay, so this file is given to you as a starter file. Okay, now this data type percolation needs to support this API. So let's go through the API. So you have a constructor percolation that takes an integer n as argument and creates an n by n grid where all the sites are blocked. And the way you do this is by creating a two-dimensional array of booleans of size n. Okay, so that boolean array is going to represent an n by n grid where all the sites are blocked. Then you have this method called open that takes an int I and an int j as an argument, and the method is supposed to open the site ij. Okay, and then you have the method is open that takes an I and a j as an argument, and this method is supposed to tell you whether or not the site ij is open or not. Okay, and then you have the method is full that takes an I and a j as an argument, and so it's supposed to tell you whether or not the site ij is full. Now remember that a site is full if it is connected to an open site in the top row via a chain of neighboring open sites. All right, and then you have this method called number of open sites that simply returns the number of open sites in the system, and then finally you have this method percolates that tells you whether or not the system percolates. All right, now, when you implement this data type, you need to take care of the corner cases that are listed here, and then you also need to make sure that your implementation meets the performance requirements that are stated here. Okay, so the constructor should take time proportional to n square, where n is the size of the grid, and then all the other methods should take constant time plus a constant number of calls to the methods from the UnionFind API. All right, and what this means is that these methods, right, they should be implemented in such a manner that they don't depend on the size of the system, which is n. Okay, and the way to achieve this these performance requirements is using the UnionFind data structure. So let me talk about that next. So I'm going to consider a very simple percolation system that is 3 by 3. All right, and let me first draw that system. So here it is. So it has 3 columns and 3 rows. Okay, and I is going to take on values 0, 1, and 2, and j is going to take on values 0, 1, and 2. Alright. Now the sites here are identified using a pair of numbers. So this site here is 0, 0, this one is 0, 1, this one is 0, 2, this one is 1, 0, and so on and so forth. Okay. Now if we want to use the UnionFind data structure to implement this data type, then you want to map a site ID here, which is a pair of numbers, to a site ID in the UnionFind data structure, which is just a single number. Okay, so what you first want to do is in the UnionFind data structure, represent these sites using the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. And there is a reason why we are starting at 1 instead of 0, and I'll say something about that later on. Okay, so you first want to map a site ID in the grid to a site ID in the UnionFind data structure, and the way you do that is by implementing this private method called encode in percolation.java that takes two arguments, an int I and an int j, and returns an integer. Okay, so given a pair of numbers representing a site in the grid, it's supposed to represent an integer representing a site in the UnionFind data structure. So for example, if I is 1 and j is 2, this method is supposed to return 6. Okay, all right. And now let's open some sites in this system. So by default, all of them are closed. Let's just open some of them. All right. Now, when you open a site, let's say we open this one, what you need to do is you need to check its neighbors, the neighbors to the left, to the right, above and below, and see if there are any open sites around. And if there are any open sites, you need to connect this open site to them. Okay, and the way you do that is by using the union method from the UnionFind API. All right. So in this case, then there are no open sites neighboring this site, so so we need not do any union operation. So now let's say we open this site. All right. So here again, this is not connected to any open site above, to the left, to below, or to the right, so we don't have to perform any union operation. Now let's say we open this site. So here again, there is no need for any union operation. Now let's say we open this one. So here you do have an open site above, so you need to make a call to the union method from the UnionFind API to connect these two sites. Okay, and then finally, let's say we open this site. So here there are two open sites that are neighboring this site. So there is one above and then there is one to the right. So you want to establish a connection between these two guys and these two guys using the union method from the UnionFind API. All right. Okay. So we have these sites open. So now let's go back to the API and see how we fare on the performance requirements. Okay, so with the constructor, we are good because we do meet this performance requirement. All that we are doing there is setting up the two-dimensional Boolean array of size n, so that takes time proportional to n square, so that's fine. Now what about the open method? Well, if we do it the way we just talked about, even that meets the performance requirements. Okay. Now what about the isOpen method? Well, that's fairly trivial, so you just have to check if a particular site ij is open or not, and that can easily be done in constant time. What about the method isFull? Well, remember that a site is full if it is connected to a site in an open site in the top row via a chain of open sites. So if we want to check if let's say this particular site is connected to an open site in the top row, then what we have to do is we have to use the UnionFind method called connected, um, to see if this site is connected to any of the sites in the top row. But that would involve scanning the top row, right? So that operation is not quite a constant time operation, because if the size of the system is n, in the worst case we have to examine n uh, sites in the top row. Okay, so with that method we don't meet the performance requirement. Okay, and then what about the number of open sites? Well, that's straightforward, because as you're opening a site in the open method, you can simply keep track of the number of open sites so far, and all that you have to return here is that number. Okay, so that's fine. That's not an issue. What about the percolates method? So here what we want to do is we want to scan this particular row and see if there is any open site that is connected to any of the open sites at the top, right? That's what it means to say that a system percolates. But this method, but that implementation again is no good, because it does not meet the performance requirement, because you have to scan this row, and then and for each such value you also have to scan this row. Okay, so that operation will certainly depend on the size of the system. Okay, so that approach is not good. Okay, so we have to do things somewhat differently. All right. Okay, so let's talk about that. But before I do that, let me just say that this system clearly percolates, all right? Because you have, this open site that is connected via a chain of open sites to the open site here in the top row. Okay, so if I pour something here, then it's going to reach here, it's going to reach here, here, and here. So this system does percolate, all right? So how do we solve this problem such that we meet the performance requirements for the data type? Okay, so what you need to do is take the system. So I'm going to redraw the 3 by thrice system from above. Okay, so you have J that takes on values 0, 1, 2. I takes on values 0, 1, and 2, and then you have the IDs 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, and now what you need to do is introduce a virtual site here. Okay, that is going to be called the source, and that's going to have an ID 0. Okay, now so that's the reason why we wanted to start this guy at 1 here. Okay, so it's this virtual site that's going to take on the ID 0, and similarly you need to introduce a virtual site here that's called the sink, and that will take on the ID 10. All right, now keep in mind that these virtual sites, they are not part of the original system at all. All right, that's why they're called virtual. So they're only part of the UnionFind data structure. Okay, so if the system is an n by n system, then in the grid you have n square sites. But in the corresponding UnionFind data structure, you're going to have n square sites, right, corresponding to these guys here. But in addition, you're going to have one for the source, which is a virtual site, and one for the sink, which is also a virtual site. So in the UnionFind data structure, you're going to have n square plus 2 sites. Okay. All right. Okay, so now what you need to do is once you have the source and sink site, you need to simply connect them using the UnionFind method union. You need to connect the source to each site in the top row. Okay, so I've just connected them like that. And similarly, you need to connect each site in the bottom row to the sink site. All right, so you do something like that, and you can do this in the constructor of the percolation data type. Okay, all right, So now let's do what we did with the system here. Let's open some sites, all right, and let's do it in the same order that we did in this case. All right. So I'm going to open this site first. All right, and then I'll open. So this is you know uh, not connected to any of its neighbors, so there's no union operation that's needed here. Then let's say we open this one, so here again no union operation is needed. Then let's say we open this one, and finally and then let's say we do open this one, but here this is connected to this guy, so you need to union these two sites. Okay, and then finally let's open this guy. So here again, it's connected to two neighboring open sites. So you have to union these guys and these two guys. All right. Okay. So let's say those are the sites that we open. All right. So now the question is, how do you figure out, if a particular site is full? Because remember that with this implementation, the is full operation did not quite meet the performance requirement. Whereas what do you do here with the is full operation? Well, all if you want to check if a site is full, all that you need to do here is check if that site is connected to the source site. Okay, and that is something that can be done in constant time. Right, it does not depend on the size of the system at all. Okay, so isFull can be implemented very efficiently. What about percolates? Because remember that with this approach, even the percolates was a problem, right? But what about using this approach? Well, here, if you want to check if the system percolates or not, all that you have to do is see if the sink is connected to the source. So here again, it does not, if you do it that way, then it does not depend on the size of the system at all, so you can do it in constant time. All right, so that's how we meet all the performance requirements. So if you introduce the source and sink virtual sites, then all the operations, apart from the constructor of course, can be implemented in constant time. Okay. All right, so now let's see, if this system percolates or not. Well, let's pour something here. So it is connected to this open site, so it's going to reach here, which is connected to this guy. So it's connected to this, it's connected to this, and that's connected to this. But there is a small problem here. All right, so now there is an open site here which is also connected to the sink, so this substance is going to flow up into that site, and that is something that we don't want. All right, and this is what we call the backwash problem. Okay, and so you need to somehow avoid this problem. All right, so we want to follow this kind of an approach with the virtual sites, so that all the operations, so the data type can be implemented in such a manner that it meets the performance requirements. But when we do that, there is this pesky aspect, which is that of the backwash problem. Okay, so you need to take care of this. You need to guarantee that this doesn't flow back up into this site here, and avoiding this problem is tricky. Okay, so you don't have to write a lot of code, but there is a lot of thought involved. All right, so I'm going to let you guys have fun with that, and make sure that you try and avoid the backwash problem. Okay. All right, so that's how you implement the data type. Um, so once you have your data type implemented, you can test it by saying Java percolation and giving it some input via stdin on the command line. All right. So here what we are doing is we are using this sample input file that is called input10.txt. So let's take a look at that file. Um, Okay, so what you see in here are you see the size of the system, so that's 10. So we're looking at a 10 by 10 system here, and then you see these pairs of numbers. Okay, so these pairs represent the sites in the grid, in the 10 by 10 grid, that are going to be opened in this order. All right, and then we want to see if whether or not this system percolates. Okay, so this is an example of a system that percolates, and then there is a version of the file which is called uh, input10-no.txt, and that's an example of a 10 by 10 system that does not percolate. Okay, so when you run your percolation implementation using input10.txt as the input, then if your implementation is correct, it's supposed to print this information, which says that 56 sites were open and that the system percolates. And if you run your program with the input10-no.txt, then it's supposed to print this message saying 55 sites were opened and that the system does not percolate. Okay. Now, in addition to the test client that is given to you in percolation, you also are given two visualization clients. Okay, one is called percolation visualizer, and the other one is called interactive percolation visualizer. And I strongly encourage you guys to use those clients for testing and debugging your percolation implementation. Okay, so let me do a quick demo of that. So let me say Java percolation visualizer, and let's give it the file input10.txt. Okay, and when you run it, this is what you will see. Okay, so the sites are being opened in a certain order, and then at the end, the program spits out. You're supposed to see some message here. So in this case, there were 56 sites that were opened and all, and this system percolates, as you can see here. So if your implementation of percolation is correct, then you ought to see an end state that looks like this. Okay, and here notice that the implementation of percolation that I have does handle the backwash problem, so nothing sort of backwashed into these open sites here. All right, because there is a virtual sink here, so if you don't take care of the backwash problem, then things would backwash into these open sites. All right, but that's not you don't see that here because my solution does take care of the backwash problem. All right. Okay, so that's how you run percolation visualizer. Now let me demo the other interactive client, which is called interactive percolation visualizer, and this one takes a command line argument, which is the size of a system. So let me say 3, and when I run it, this is what I see. So this is a 3 by 3 system where all the sites are initially blocked. Okay, and it says there are 0 open sites. Okay, and here on the terminal you see the number 3, which is the size of the system. Now I can click on a site here to open it. So let me click this one. So I just opened the site 01. Okay, and it's now full because there is a source that sits here and I've poured something there, and that has seeped through into the site. Now let me open some site. Let me open this one. So it says 1 2 was opened. Let me open this one, which says 2 0 was opened. Now let me open this one, so that's 2 2, and now let me open this one. Okay, and when I do that, what will happen is this whatever I poured into the source is now going to flow into that cell, and then into that one and that one. All right, so the system then does percolate. So I have opened 5 sites, so that's what you see here, and the system percolates. So here again, there is no backwash. Okay, so nothing has sort of flown back into this open site here. Okay, so that's another very interesting client that you should try and use when you're trying to implement and debug your implementation of a percolation data type. Okay. All right, so that's problem one. So now let's move on to problem two. So this is where you want to estimate the percolation threshold P star. All right, and to do this, we are going to make use of the percolation data type that we just implemented in problem one. All right. So to estimate the threshold, what we're going to do is we're going to perform a certain experiment many times and average the results to get an estimate of P star. Okay, so what is the experiment that we want to perform? Well, it's this experiment. It's a Monte Carlo simulation experiment, and this is how it works. Okay, so you create a percolation system of size n, so you would use your percolation data type for that, and then what you do is you repeat these steps until the system percolates. Okay, meaning you choose a site ij at a random, okay, among all the blocked sites, and then if it's not and then you simply open it. Okay, so this is essentially a call to a method in the percolation data type. Okay, so you keep doing this until the system percolates. And remember, again, you can check if the system percolates or not simply using a call from the percolation data type. All right. And once the system percolates, what you need to do is calculate the fraction of sites that were opened. Okay, until percolation, and that fraction is going to be an estimate of the percolation threshold, okay, from a single experiment. So for example, let's take this 20 by 20 system. So here what you see are different snapshots of this system when 50 sites were opened, and then 100, and then 150, and then 204. So when the 204th site was opened, the system suddenly went from not percolating to percolating. Okay, so that's when you're out of this loop, and you calculate this fraction as simply 204 divided by the size of the system, which is 20 times 20, right? So that's 400. That's because you're looking at a 20 by 20 system. So that fraction is 0.1, and that is our estimate of the percolation threshold from a single experiment. Alright, so now to get a robust estimate for the threshold, we just need to repeat this experiment many times and take averages. Okay, so that's exactly what we're going to do. So we want to repeat this experiment capital T times. Okay, and then we'll simply average the results to get an estimate for the percolation threshold. So let's say that in the experiment little t, you got x sub t as the fraction of open sites until percolation. Okay, so then you can calculate the mean or the average value of percolation threshold as mu equals x1 plus x2 and so on all the way up to x sub capital T divided by capital T. Okay, and once you have the average, you can calculate the variance, which is going to give you the sharpness of the threshold, and the variance is simply calculated using this expression here. Right, it's the standard formula for mean and variance. Okay, now once you have these guys calculated, then you can also calculate what is called the 95% confidence interval for the percolation threshold, and that is simply an interval given by this lower bound and this upper bound. Okay, and what the confidence interval tells you is that if I repeat this experiment many times, then about 95% of the time the percolation threshold is going to be within this interval. Okay, so that's what the confidence interval is telling you. All right, now we're going to perform these experiments using a data type called percolation stats, and that's going to have this API. All right, so it has a constructor called percolation stats that takes two arguments n and t. So the constructor is supposed to perform t independent experiments of each one being the experiment that we just described on an n by n grid. Okay, and then it needs to save all the fractions, the x sub t's in some array. Okay, um, and then you have methods for calculating the mean. So this method simply returns the mean of the percolation threshold. You have this method that returns the standard deviation of the threshold. This one that returns the low end point of the 95% confidence interval, and this one returns the high end point of the confidence interval. Okay, so that's that. Um, okay, and so this part is fairly straightforward. So once you have the percolation data type implemented from problem one, implementing percolation stats in problem two is pretty straightforward. Okay. Uh, all right, and once you have percolation stats implemented, you can test it by running this command on the terminal. So the first argument here is n, the size of the system. The second argument is capital T, which is the number of experiments that you want to perform. Um, and then when you do that, the program is supposed to print something like this. So it needs to print the mean value of the percolation threshold, the standard deviation, the low end point of the confidence interval, and the high end point of the confidence interval. Okay. All right. So that's problem two. And now, just keep in mind that under the data directory you will find some sample files that you can use along with the percolation clients, either the test client and percolation.java, or along with the interactive client percolation visualizer. Okay, now if you look in that directory, you'll see that associated with most input text files, there are also the output.png files that show the desired output. So let me show that to you. So you have, for example, here an input file that is called snake13.txt. So that's the input. So it's a 13 by 13 system, and the sites are going to be opened in this order. And when you run that through percolation visualizer, at the end you ought to see this as the output. Okay, so at the end you want to see this image, and then you have to see the message that says 85 open sites, and that the system percolates, because the system does actually percolate, right? Okay, so that's that. And then there are many such examples, and you should try and test your programs against as many examples from here as possible. Okay. All right. And now the files that you want to submit are percolation.java, percolationstats.java, and report.txt. But before you submit your files, make sure that your programs meet the input and output specifications, and you can do that by running run tests on the terminal by giving it the problem number that you want to test, or if you omit this argument, it's going to test all the problems. Okay, so let me demonstrate that. So if I run test without any arguments, it tests all of the problems, and if your particular solution is correct, then you ought to see the message pass in green, and if it is not correct, then you'll see the message fail in red. Okay. Now if you just want to test one problem, let's say problem 1, then you specify the number as an argument, and in that case it simply tests problem 1. Okay, so that's that. Now the next thing is, before you submit your programs, make sure that they meet the style requirements, and the way you can do that is by running check style on a program. So I can say check style percolation.java. Okay, and if the program is correct in terms of style, then you ought to see just these two messages. But if there are issues, then the program will come back with messages that tell you that such and such style was violated, and then you can go about fixing that. All right. And then the last thing is, do remember to write a report for the project. And for the report, you want to use this template. And in your report, I need to know, how much time you spent on the project. So that information goes there. Then I need to know, in like a few sentences, how you approached each problem. Okay, how you approached each problem, the issues you encountered, and how you solved those issues. So please tell me about that in this section here. And again, I just need like a few lines for each problem, like a short paragraph for each problem. All right. And then in this section, I need to know about the help that you received, okay, from other people. So so if you received help from someone, I need to know who that person was that helped you. I need to know that person's status, meaning whether that person was your classmate, a CS210 grad, or a TA, or someone else. Okay, I need to know that. And in addition, I need to know in like a few words about the nature of help that you received from that person. All right. So this section is extremely important. So if you receive help from anyone on this project, I need to know exactly what that help was. Okay. All right, and then finally in this section, feel free to list any other comments that you may have. Okay, and I would love to hear from you. Whether you learned anything from this project, and whether or not you found this project enjoyable. Okay, so if you have some to say something about that, so this is where you need to mention it. Okay, all right. So that's the report. And then the last thing is, yeah, just make sure that your report doesn't exceed 400 lines, and that it doesn't contain spelling mistakes and so on. And very importantly, make sure that it doesn't contain lines that exceed 80 characters. So make sure that you wrap your lines around by hitting the enter key, and by making sure that they're all within the 80 character limit. Okay. All right, so that's all that I had to say for project one, and I hope you have fun doing it, and I hope that you learn something from it. Okay, so all the best. Thank you. Bye.